All right, kids, we're back looking at the classic. It's a classic ballistic pendulum. It's used a lot to talk about the concept of collisions and conserving momentum. And so we've got this bullet, which I've drawn red. It's moving with a speed v. Its mass is little m, and it's about to hit this piece of wood that's being held up by these two strings, and the strings are 90 degrees to the piece of the wood. The strings are straight up and down, completely vertical, and the wood has a mass big M. It's not moving. So the first question is in page 253, section question 5.3, section question 7. It says, explain why the horizontal momentum, and the key word there is horizontal. They even put it italicized. Explain why the horizontal momentum of the bullet wood system is conserved during the collision, even though the strings exert tension force on the wood. Well, that is true, but a couple things you've got to realize here is that the collision takes place very quickly. Very quickly. The mass has inertia, the string has inertia, so it would take a while for any reaction to occur in the wood as the collision happens. So the duration of time that the bullet and the block are during the duration of the time that the bullet and the block are interacting, the strings are vertical. See? And only balance gravitational force. There's no force from these strings that are horizontal during that initial collision that's happened so quickly. All right, so they're not going to slow down the movement of the wood in a horizontal way at all. So the next thing is during the collision, not during the swing, momentum is conserved. So really what they're telling you in a sneaky way here is that there's two parts to this question. There's the collision part, all right, and then there's the swing part. So if you're going to study this thing in its entirety, first you deal with the collision part, then you deal with the swing part. Now, part B says if the bullet and the wood have a mass little m and big M, and I've drawn that, right? Little m and big M for the masses, and the bullet has an initial speed v, so speed of bullet before the collision is v, right? And the wood's not moving, so the speed of the wood before the collision is 0. Remember, we're doing the collision part here, okay? It says derive an algebraic expression, an equation, basically, for the speed of the bullet and the wood immediately after the collision, okay, before the swing upward. So we want to express this new speed in terms of the two masses and in terms of the speed of the bullet as it was approaching the wood. So what I'm telling you here is that we want to find velocity prime. That would be the velocity of the wood and the bullet together as they take off, velocity prime. And how are we going to do that? Well, it's a collision. And during collision, momentums are conserved. So the momentum after the collision is equal to the momentum before the collision. All right? So momentum after the collision is the speed with which this new bullet wood combo system object move at times the mass of the wood and the bullet together. So the wood and the bullet together, their mass, and the speed with which both of them move together as a system, which we're going to call V prime. That has to equal the momentum before the collision. Well, the momentum before the collision was simply the bullet's momentum. So we have mass of the bullet multiplied by the speed of the bullet before the collision, VB. So we do a little rearranging here and we get velocity of the system, the bullet and the wood together after the collision is equal to the mass of the bullet times the speed of the bullet before the collision all over the mass of this new system, which is the mass of the bullet plus the mass of the wood. But the textbook says, look, the velocity of the bullet before the collision is just v. So I changed v, velocity of the bullet before the collision, to just v. And here is your solution to part B. On to question C, kids. On to question C. As the bullet and the wings swing up, what law of nature can be used to relate the maximum vertical height to the speed just after the collision? Well, it's the law of conservation of energy can be used to relate the maximum vertical height to the speed just after the collision. Basically, what the bullet has done has started the pendulum at the bottom and started the motion of the pendulum. Usually when we've done pendulum motions, it starts up here and we let it go and swing down. Big deal. We've used a bullet to start the motion up here and it swings up until it stops. In the past, we've used the law of conservation of energy on pendulums. Now we're using it on a pendulum again, just with a different way to start the motion of the pendulum. So we're on to part D of the question. It says use your answers in B and C to derive an expression for the maximum vertical height in terms of the mass of the bullet, the mass of the block, how the speed of the bullet before the collision, and the gravitational field strength near the surface of the Earth, the magnitude of that. Well, here we go. Here's what happens. The bullet hits the block of wood, and the block of wood swings up so that it gains a height h. That's what I've drawn here. We're going to use the law of conservation of energy to solve this. So total energy initial is equal to total energy final. Well, the total energy before the swing starts, or just as the swing starts, is the kinetic energy right here, just as the collision ends and the swing begins. It has no height here. It's all the starting motion caused by the bullet. So the total energy initial is kinetic energy initial. Then it swings up and stops. As high as it's going to get is h. So the total energy final is all gravitational potential energy, EGF. Okay, so let's keep that in mind. It's just a conservation of energy question. So the next thing we do is we write out the equation for kinetic energy of this system, which is half the mass of the system, which is bullet, wood mass together, times the velocity of the system after the collision, or the speed of the system after the collision, I should say, v prime, and we have to square it because we know the equation for kinetic energy, half mv squared. At the end, it's all gravitational potential energy, so it's the mass of the system times the magnitude of the gravitational field strength near the surface of the Earth times its newfound height. Well, look, kids, the mass term in the bracket on each side cancels out. So we're left with v prime squared over 2 and gh over here. I divide each side by g, and I get that the height is v prime squared all over 2g. But remember, I have an expression that I calculated in part B. I have an expression that I calculated in part B that v prime is mass of the bullet times the speed of the bullet before it collides with the wood all over the mass of the system. So what I'm going to do is I'm going to take this and plug it in for v prime, and that's what I've done there. I plugged it in. Okay, then I do some squaring here, and I put together everything that's in the denominator, and I come up with an expression for the height in terms of the mass of the bullet, the speed of the bullet before it hit the wood, the gravitational field strength's magnitude, and the mass of the wood and the bullet together. So we have solved question, or part D, I should say. And from here in the red to here to the blue is just some algebra. Take your time with it. You'll be able to figure it out. It's good practice for your brain. All right, well, part E wants us to rearrange it for V, the speed of the bullet before it hit the wood. So they want us to take this expression and solve for V, isolate for it. Well, the easiest thing to do is get rid of the denominator here that's affecting the V. So multiply each side by the denominator. It'll clear out on this side and leave us with m squared v squared. And it'll come over to this side and multiply the h. And that's what we've done there. Then we're left with m squared v squared. We still want to isolate for the v, so we divide both sides by m squared. And that's what we've done there. And that'll leave us with this term right here. I've just done a little rearranging. I brought the 2, the g, and the h together out front. Makes it look nicer. I still have the m plus m squared and still the little m squared in the bottom. Now we're going to square root both sides. So we square root both sides, gets rid of the square here, gets rid of the square on the bracket, and we have a root 2GH out front. Root 2GH, a very familiar expression in the world of conservation of energy with kinetic energy and gravitational potential energy. And the final one I assigned, because I did not assign G, I just assigned F, is use that equation. If we know the mass of the bullet, and we do know the mass of the bullet, if we know the mass of the wood, we know what planet we're on, we know how high it swings after the collision, we plug all of that into here and we get our final answer. There you have it. I'm really glad we were able to do this question. It's a classic. And once again, thanks for everybody for working hard, paying attention, logging in. All right. The principal sent all the teachers at West Lane a email a few days ago saying the building's closed, but school continues. I want to thank everyone who's kept that mentality going during this time. All right. Take care of yourselves. Enjoy. Have a good long weekend. Be safe. Bye bye.